In this video, we'll discuss what an integrated rate equation is, how we can get one from the actual rate equation, and how we can graph reaction data and use the graphical analysis to figure out what kind of rate equation we have and how to extract the rate constant. If we look at basic rate equations, you can see they have some form like this. We might have a 0th order reaction. So let's imagine we have a reaction that's 0 order in A, and since anything to the 0 is 1, we could just write that that is equal to K. So a 0 order reaction actually has a constant rate. Or we could have a reaction that is 1st order in A, and we may or may not write the 1, since if we could just write V is equal to Ka, it would mean the same thing. Or we could have something that's 2nd order in K. Okay. So in all of these cases, we're talking about how fast the reaction goes as a function of the concentration of this reactant A. We're not actually giving how A varies as a function of time. But the integrated rate equation actually gives you that. It gives you how does the concentration of some reaction component vary as a function of time. So what we'll do is we'll just do all three types of reactions, 0th, 1st, and 2nd order reactions, and show how we can get an integrated rate equation. We'll start with 0th order. So a 0th order reaction, V is equal to K, and this is actually a differential equation. We could rewrite this, remember, if we have a reaction that, say, is A goes to 2B, we could say V is equal to negative the slope of the concentration of A with respect to time, and we just said that was equal to K. Well, this is a differential equation. It's actually a pretty easy one to solve. Since calculus and differential equations aren't required for my course, I'm going to just solve the differential equation and just present the results. But be aware that's all we're doing is just solving this simple differential equation. All right, if you solve this simple differential equation, you get this equation. You get that the concentration of A is equal to the concentration at the very start minus K times T. So that's the result of just two steps of solving that differential equation. So this is an integrated rate equation. So notice it doesn't have slopes in it, it just has concentrations as a function of time. So we can imagine looking at this and seeing how we could graph it and get K, because if we graphed our A as Y and our T as X, and our A naught, our original concentration, as our y-intercept, we can see that this is a constant and this is a constant, so we could just call minus K our slope, and see we have y equals mx plus b. So this means if we just graph concentration as a function of time, if we get a straight line, we can see what the slope is. Look at our equation. Slope is negative K. And that will all be true, that we'll get a straight line for this type of graph only if it's 0 order reaction. So as soon as we see this kind of graph and see that the slope is straight, we know it's 0 order in A. Okay. All right. So make sure that you've got that sort of equality in your head. That 0 order in A if you graph A as a function of t and it's a straight line. Okay. All right, let's move on from 0 order to 1st order. So once again, we've got some reaction where A is reacting to form some products, and we're going to look at how to get an integrated rate equation. So the rate equation here is that V, the reaction rate, is just a linear function of A, and once again, we could also say that the rate here is just minus dA dt. And so once again, this is a differential equation. If we solve that, we get that the concentration of A is equal to the original concentration of A times this decreasing exponential. And we can see, well, if we graph that, we graph A concentration as T, we get a nice exponential plot. It's sometimes useful to see what kind of plot would give us a linear line, a linear curve though, straight line. So let's take the log of both sides. If we take the log of both sides, we end up with the log of the concentration being equal to the log of the original concentration, and then we have a minus KT term. And once we've manipulated the equation this way, we can see, oh, we could call this y, we could call this the y-intercept b, this would be our x, and this leftover bit here would be our slope, so y equals mx plus b. So we can see what kind of plot would give us a straight line for a first order reaction, and that would be graphing the log of the concentration, not the concentration. And if we do that, we can also see how we can pick up the number of the rate constant. It would just be the negative of the slope here. Great. So we can see this kind of graphical analysis can also give us our rate constant for first order reactions. So this is first order in A. So this would only be true if the reaction was first order in A. Okay. All right, so let's move on to second order in A. Okay, so we write the original rate equation. It's second order in A, so we've got this square here. And for this reaction, we can see that the rate is defined as the negative of the slope of A with respect to time. So we've got another differential equation. If we solve this one, we get 1 over A is equal to 1 over A naught plus KT. So we can see how we can make a straight line plot out of this. If we plot this as our y and t as our x, then our slope is just going to be our rate constant. And our y-intercept is going to be 1 over A naught. So if we plot this, we can see we want to just have time on the x-axis. We want to have reciprocal concentration on the y-axis. We can see our slope is just going to be our rate constant, so we're going to have something like this. And it looks a little bit counterintuitive, but remember that this is reciprocal concentration, so this represents concentration going down. So we are eating up our reactant, and slope is equal to K, and our y-intercept here is going to be 1 over A naught, the reciprocal of our original concentration of A. Great, so if you have this kind of graph being linear, then you can say it's second order in A, the thing that you're graphing the reciprocal of. All right, now we do have to be a little bit careful here when we do this kind of analysis, and the reason, I'll give you a caution on the next slide, and that's that suppose that you have something that's first order in A. So it has a nice exponential decay here. And you take data over this time interval. If we zoom in enough, that's going to look like a straight line. And so you might think it's 0th order. So if you're going to use integrated rate equations to figure out the order of a reaction, you have to do a long time course. Don't just do maybe a fraction of a half-life. You want the concentration to decrease quite a bit, maybe 80 or 90%, so you can detect the curvature that will be there. Okay? Otherwise, you could be fooled into thinking the line's straight when it's not.